Imagine a streak of fire tearing across the sky, a brilliant white trail against the deep blue, launched with a ground-shaking roar. This isn't just a firework, it's a marvel of engineering, capable of traveling thousands of miles with precision. From ancient arrows to today's missiles, every step in science has led to this moment. The launch of a missile is a symphony of thermodynamics, aerodynamics, and computer science in action. Unlike ancient projectiles, a missile carries its own engine, fuel, and brain, making it an autonomous, self-guided machine. This ability to guide itself is what makes a missile one of the most sophisticated technologies ever created. Today we'll peel back the layers from explosive thrust to the electronics that guide its path. Understanding missiles isn't just about military hardware, it's about the science that shapes our world. So put on your safety goggles. We're diving into the amazing science of missiles. You might hear the words rocket and missile tossed around as if they mean the same thing, especially in movies or news reports. But while they might look similar and both shoot through the sky with incredible speed, there's actually a big difference between the two. The terms are often confused, but they're not interchangeable. Understanding the distinction helps us appreciate the technology behind each one. Here's the key. All missiles are rockets, but not all rockets are missiles. The main thing that sets them apart is guidance. Think of it this way, guidance is what gives a missile its smarts. A rocket is any vehicle or device that uses a rocket engine for thrust. This includes everything from the fireworks you see on New Year's Eve, to the mighty Saturn V that carried astronauts to the moon, to the simple bottle rockets you might launch in your backyard. Rockets are essentially powerful tubes filled with fuel. Once they're launched, they go wherever the initial force and the wind take them. They don't have any way to change direction mid-flight, no brain, just raw explosive power pushing them forward. A missile, on the other hand, is like a rocket with a mind of its own. It's equipped with a guidance system, an onboard computer, sensors, and sometimes even radar, that allows it to steer itself toward a specific target, even if that target is moving. Imagine throwing a paper airplane. Once it leaves your hand, it glides wherever you aimed it, just like a rocket. Now picture that same paper airplane, but with a tiny pilot inside, holding a steering wheel and making adjustments as it flies. That's what a missile does. It can change course and home in on its target. This guidance system transforms a simple projectile into a sophisticated weapon, capable of tracking and hitting targets with incredible accuracy, even in challenging conditions. For example, the AIM-120 AMRAAM missile uses advanced radar to lock onto moving targets, constantly adjusting its path in real time to ensure it hits exactly where it's supposed to. Rockets are the backbone of space exploration, powering satellites, probes, and astronauts beyond Earth's atmosphere. Missiles, meanwhile, are designed for precision and purpose here on Earth, often used in defense and military operations. So, the real difference comes down to intelligence and adaptability. Rockets rely on sheer force, while missiles combine that force with smart technology to achieve their goals. Next time you see something launch into the sky, ask yourself, is it just going up, or is it heading somewhere specific, guided by technology? That's the easiest way to tell a rocket from a missile. One is all about power, the other is about precision. It's a fascinating distinction that highlights how far technology has come, from simple tubes of fuel to intelligent machines that can change the course of history. Every missile, no matter its size or purpose, relies on a powerful engine at its core. This engine is what gives the missile its life, its speed, and its ability to reach distant targets with precision. The system responsible for this force is called the propulsion system, and it's the driving force that pushes the missile toward its target, overcoming gravity and air resistance. There are two main types of propulsion systems used in missiles: rocket motors and jet engines. Each has unique strengths and is chosen based on the mission's requirements. Rocket motors are completely self-contained, carrying both their fuel and oxidizer inside. This means they can operate in the vacuum of space, making them ideal for ballistic missiles that travel outside the atmosphere. Solid fuel rockets are known for their simplicity and reliability. They offer instant power and can be stored for long periods, ready to launch at a moment's notice. Liquid fuel rockets, on the other hand, provide more control over thrust and can be throttled or shut down if needed. However, they are more complex and require careful handling and fueling before launch. Jet engines, like those found on cruise missiles, work differently. They need to breathe air from the atmosphere, which makes them highly efficient for long, low-altitude flights within the Earth's atmosphere. The Tomahawk cruise missile, for example, uses a jet engine to travel vast distances, flying close to the ground and following the terrain to avoid radar detection and enemy defenses. Choosing the right propulsion system is always a trade-off. Rockets deliver incredible speed and altitude, making them perfect for quick strikes and space travel. Jets, meanwhile, offer greater range and fuel efficiency, ideal for missions that require endurance and stealth. Some advanced missiles even combine both technologies, using a rocket booster for the initial launch phase and then switching to a jet engine for sustained cruising, maximizing both speed and range. Engineers carefully select and design propulsion systems to match each missile's mission profile. Whether it's speed, range, altitude, or the environment it will travel through, every detail matters. Propulsion truly is the heart of the missile, where science and engineering come together to turn ideas into reality and match technology to purpose. It's a perfect example of how engineering innovation solves real-world tactical challenges, pushing the boundaries of what's possible. In the end, the right engine makes all the difference, determining not just how far a missile can go, but how effectively it can accomplish its mission. Propulsion gets a missile moving, but guidance tells it where to go, the missile's brain. While engines provide the raw power, it's the guidance system that transforms a simple rocket into a precision weapon, capable of hitting targets miles away with astonishing accuracy. Without guidance, a missile is just a blind rocket, unable to adjust its path or respond to changing conditions. It might travel fast and far, but it has no way to find its mark. GPS guidance uses satellite signals to steer missiles to precise coordinates, ideal for stationary targets like enemy bunkers or infrastructure. By constantly updating its position, the missile can make tiny course corrections mid-flight, ensuring it arrives exactly where it's needed. Radar guidance lets missiles track moving targets, using radio waves to see and follow aircraft or ships. This technology allows the missile to lock onto fast-moving threats, even in poor visibility or at night. Some missiles have their own radar built in, scanning the skies for targets, while others rely on external sources like ground stations or aircraft to provide tracking data. Infrared guidance gives missiles heat-seeking vision, homing in on the hot exhaust of engines. This makes them especially effective against aircraft, as the intense heat from jet engines stands out clearly against the cooler background. Laser guidance involves a friendly unit painting the target with a laser. The missile follows the reflected light. This method is highly accurate and is often used for striking high-value or moving targets in complex environments. Each method has its own strengths: GPS for pinpoint accuracy over long distances, radar for tracking moving targets, infrared for heat-seeking attacks, and laser for precision strikes guided by ground forces. Modern missiles often combine these systems, switching between them as needed for maximum effectiveness. This multi-mode guidance makes them adaptable to a wide range of missions and countermeasures. The guidance system is what makes a missile smart, adaptable, and deadly. It's a blend of sensors, computers, and software working together in real time to outthink defenses and ensure mission success. It's the difference between hitting a general area and striking a specific target with surgical precision, minimizing collateral damage and maximizing effectiveness. The brain of the missile is a marvel of modern electronics, representing decades of innovation and engineering. It's this technology that gives missiles their reputation as the ultimate smart weapon. Guidance tells a missile where to go, but control systems make it happen. They're the missile's muscles. Most missiles use fins and wings to steer, adjusting airflow to turn, climb, or roll. Actuators move these surfaces with incredible speed and precision. At high altitudes or for sharp maneuvers, thrust vectoring swivels the engine nozzle, pushing the missile in new directions. Some use small side thrusters for fine adjustments, especially in space or for hit-to-kill interceptors. These systems ensure the missile flies with agility and purpose, not just speed. Control is what turns guidance into action. All the missile systems exist to deliver the warhead, the payload that creates the intended effect. Not all warheads are about big explosions. Each is designed for a specific mission. High explosive warheads create powerful blasts and shrapnel, devastating soft targets. Shaped charges focus energy to pierce armor, while kinetic penetrators use sheer speed and mass to smash through defenses. Thermobaric warheads create massive fireballs and pressure waves, effective in enclosed spaces. Some warheads are non-lethal, designed to disable electronics or infrastructure. Each is a carefully engineered solution to a unique challenge. The warhead is the final piece of the missile's scientific puzzle. As soon as guided missiles appeared, so did countermeasures, a technological arms race of offense and defense. Heat-seeking missiles are fooled by flares, hot, bright decoys that lure the missile away from aircraft engines. Radar-guided missiles are countered with chaff, clouds of metallic strips that confuse radar, or with electronic jamming that blinds sensors. The ultimate defense is interception systems like Iron Dome or Aegis use radars and interceptor missiles to shoot threats out of the sky. Hitting a missile with another missile is like hitting a bullet with a bullet, requiring speed, precision, and advanced computing. This constant back and forth drives innovation in both attack and defense. For every new missile, a new countermeasure emerges. It's a high-stakes game of cat and mouse. The result? Rapid advances in science and technology. Countermeasures are as much a part of missile science as the missiles themselves. The race never ends. Missile technology is evolving fast. Hypersonic speeds and artificial intelligence are changing the game. Hypersonic missiles travel at Mach 5 or higher, making them nearly impossible to intercept. Glide vehicles and scramjet-powered cruise missiles push the limits of speed and maneuverability. AI is making missiles smarter, able to distinguish real targets from decoys and adapt mid-flight. Future missiles may be given missions, not just targets, using onboard sensors and AI to identify and strike the right objective. Swarm tactics are emerging. Dozens of small AI-connected missiles coordinate attacks, overwhelming defenses. Some jam radar, others identify targets, and the rest strike, all working together like a hive. This is a new paradigm in missile warfare. The future is fast, smart, and unpredictable. Missiles are symbols of power and the pinnacle of science: thermodynamics, aerodynamics, and computer engineering in action. The technology behind missiles has led to breakthroughs in materials, GPS, and computer modeling, benefiting everyday life. But this power is a double-edged sword. It can defend or destroy. The rise of faster, smarter, more autonomous missiles raises tough questions about responsibility and control. These aren't just issues for leaders, they're for all of us in a technological world. Understanding the science is the first step to informed debate and wise choices. The story of the missile is a story of human ingenuity and the choices we make. Science gives us the tools. How we use them is up to us. Stay curious, keep learning, and help shape the future. Science is the key, and it's in your hands.